Uh, okay, let's get back to our lecture. So first of all, the last maybe 2 or so weeks, we covered quite a bit about probability and also for the purpose to understand or to fully understand Kalman filtering. Okay, and last week we were almost done for the derivation of Kalman filtering. Let me briefly recap a little bit. So Kalman filter is dealing with these stochastic linear systems. Our goal is to try to estimate state given all the measurement. According to the what? Minimum mean square estimation theory, and all we need to do is try to compute the conditional expectation of x given all the measurement. Okay. As I mentioned, Kalman filtering assumption is that everything is a linear Gaussian. So every state, all the state at any given time and all the y at any given time, they are jointly Gaussian. Okay? So we are living in a Gaussian world, so we can easily compute conditional expectation. Okay? If it is not Gaussian, it will be pretty hard to compute them, especially for high dimension. Based on this, so I want you to keep in mind we're just computing this. Okay? So it's completely a what? A probability problem. All right? A lot of filtering and signal processing and communication networking. I mentioned quite a lot applications, right? And I didn't give you a detailed example. You will eventually see, hopefully I will show you some example today. They're just trying to estimate something given, estimate a hidden variable given measurement. Okay, all of them is about doing this. And eventually they're just trying to compute conditional expectation or some kind of function of the posterior distribution. Okay, the key you have to remember is that at any given time, where is it? Okay, before doing that, you should know the definition of those notations. At any given time, xk given capital Yk at all the measurement up to k. Xiaohan, how to explain this? Is this a random variable?
Yes.
What kind of random variable it is? It's Gaussian. All right, we are living in the Gaussian world. It means this is a given Yk, xk is still random, and its distribution is Gaussian. If you want to describe a Gaussian, what do you need? A mean and covariance. What is mean and covariance? Our notation means this mean is what? Xk hat, right? Covariance is pk. Okay? I hope you truly understand the meaning of these notations. There are more sits up front. Okay? You see what I mean? All we are doing is try to update this as k increases. Okay, we are deriving what the mean should be based on the system dynamics and based on our modeling assumptions. So all we are doing is to make sure we know the mean and the covariance, so we know exactly everything about the distribution of xk given yk. Okay, so last time we mentioned that typically we need to do this iteratively or recursively, and this is xk hat and pk at time k, and our goal is to compute xk plus 1 hat and pk plus 1. Right? We break up this step into 2 intermediate steps. The first one is called prediction, for which there's 2 index, right? K given k to k plus 1 given k plus 1. Both of these 2 things have different meanings, all right? So these 2 need to, we just need to change them one by one, all right? The first one is prediction. We fix the measurement. We only predict the next step. So this is what I think we were done last time on this step, right? If you don't remember, I think everyone in this room should be able to derive this. This is the simplest step. This is a very simple application of what we were doing It does not even involve Gaussian. All right, this step is simple. Prediction step is simple. The hard step is the measurement update. Okay, so we give an example to let you see a flavor of this measurement update. This example, I'm not sure how many of you review this example. I think you should review this example, try to understand everything, and then the Kalman filter step will be simple. Okay, let me summarize, add one more slide to make sure everyone can understand. I would say the key for Kalman filter measurement update step. Update step. Okay, the key for that, let's even try to move to a more generic problem with what we're doing, okay? I don't want to kind of confuse you with those sub-indices or XK hat. Let's just think about a generic problem, okay? I would say key, I would say just a key, that's fine, okay? Let's assume we have X, Y, and Z, 3 random variables. Okay, let's somehow jump outside of the a Kalman filter setup. Let's use these 3 simple notations. Jointly Gaussian, all right? Jointly Gaussian. Okay, so I will say X, Y, and Z. If we view them as a big vector, and they are distributed as a Gaussian, so with mu X, mu Y, mu Z, and some covariance matrix, you know those numbers, right, in the matrix. Suppose they are given, right? So the question I'm asking, okay, this question is related to the fundamental nature of the measurement update step, so that I'm somehow explaining this separately. So the key is that I want to make sure I want to compute my expectation of X given Y equal to Y and given Z equal to Z. There's 2 things given. Okay, there's 2 things are given. Both Y I know, both Z I also know. Do you know how to compute this? That's very simple for you, should be, all right? Maybe I'll give a test or a quiz. So this should be very easy for Gaussian because a direct approach should be easy, okay? I would say direct approach. I mentioned this a little bit last time as well. Okay, we will just view everything, whole thing, as a big vector, okay? And try to compute what? Try to compute the expectation of X given Y and Z equal to Y and Z, all right? This given we view as single given, right? They're given at the same time and specify the value, but this vector is fine, all right? And using the conditional Gaussian formula we discussed and practiced many times over the previous lectures. Okay, but we can compute this way. That's called, I would call that batch approach. Okay, we view these 2 things are given together. Okay, but Kalman filter is really about recursive. Things like recursive. And the first step, I'll try to relate, okay? Suppose I can compute X given Y equal to Y upon knowing Y equal to Y. An event happened, Y equal to Y, right? Then I update my belief about X, and X is still random. I can compute this, that's fine. Because X and Y are also jointly Gaussian. Let's forget about Z, X and Y are jointly Gaussian. You know how to compute this, right? This is also simple. Now the question is, the second step is, I want to update, further update. Y gave me some update about my belief about X. Now, in addition to Y, I receive Z, right? Upon update X given to Y and Z equal to Z, upon knowing the value of Z equal to Z. You see the difference? I break this into two steps. First, I compute Y as I know Y, right? And then Z come in. I know Z as well, but I don't want to recompute them. I want to use, the key is that I want upon knowing this, using X given Y, right? Recursively. Using my previous knowledge about X after receiving Y. That's the key. The result will give me the same result. These two, X and these two approach, there's too many 1 and 2, sorry. There's, let's call it A and B. Okay, this 1 and 2 should lead to the same result. It has to be, okay? But its key is that in this way, I can keep updating once I receive new measurement. Last time, the example I gave you, I already tell you how to do this, but I want to explain that a little bit more. Let's think about this as the following, right? I have X, Y, as Z. They are jointly Gaussian, X, Y, and Z. There is a covariance of X, right? Covariance of X, Y, covariance of X, Z, right? Covariance of Y. You know how to fill up this covariance matrix. Okay, that's original. Before I know anything, this is what my knowledge about these three random variables. Now an event occurred. Okay, event occurred. Somehow I know Y equal to Y. I know Shenzhen or Guangzhou temperature equal to 20 degrees today. Today is cooler than yesterday, right? So what happens? Then I'm into another kind of domain. I know now I'm living in the world that I see something already happened that completely changed my belief, right? I'm inside the box, and this box, after Y, I see Y equal to Y, I will say X and Z, do you know them? I know them, but I don't know them for sure. They are still random. What's their distribution? It's still Gaussian. Outside this, of course, X and Z are Gaussian. Now Y equal to small y, right? I see that. Under this assumption, under this condition, X and Z are still Gaussian. Are you with me? Okay? And this distribution will be still Gaussian. Gaussian characterized by mean and covariance. What do you think its mean will be? Is this mu x? No, I know Guangzhou is 20 degrees today, so modified my belief. And what this should be, somehow the mean is conditional mean, right? Now I'm living in the y equal to small y world. Okay, everything has changed. Okay, my belief is still in this world, and I also know mu of z is also given y. All right. Okay. So for sake of simplicity, I would ignore this a little bit. I will use a different notation. I will call this mu x tilde and mu z tilde. To distinguish, this is not okay. Now I have covariance tilde x, covariance tilde xz. Okay, this covariance matrix become 2 by 2 if x and z are scalar, covariance tutor, x and z, okay, and this is covariance tutor z and x, and covariance tutor z. You see, right? If I change this, everything becomes different, okay? Now let's look at this again. So now what happened next is that, okay, another event occurred. I know another event. What is z equal to z? But this event occurred after I know y equal to y. So I'm now in the world, this box, y equal to y world. So then I'm going to ask Su Yuan, after this event, is x and z are still random? X is still random, z is not. Z is known, all right? Z is small z now, okay? So x is still random. What's the distribution of x? Gaussian, right? So it's Gaussian. I will call this mu of x tutor, all right? Everything becomes different, right? So then this is covariance tutor x. This will be my what? Expectation of x given y equal to y, z equal to z. Okay, but how do I compute this? By using here, not jumping outside. I can directly compute this from here, okay? But I can also do recursive, this nested loop, okay? First I jump in the box. I'm living in the world of capital Y equal to small y. Then I jump into a smaller world that, I further know more information, capital Z equal to small z. Then I'm here, right? So what do you think about this? Mu x tutor equal to what? Depending on where you write this formula, if I write this formula inside this box, will be mu x tutor, given this, right? I'm treating this, right? So inside this bigger box, this nested box, okay? Characterizing the information available to you. Plus what? Covariance of xz tutor, right? Covariance tutor z inverse times z small z, sorry, the capital Z small z is a little bit confusing, but this small z times mu z tutor. Are you with me? So if I'm computing after if I here, so I know this formula using the previous estimated x and z, so that will be my formula. Okay? So that's the recursive update. If you look at this, this is what? It's the expectation of x given y equal to y. This is covariance of xz given y equal to y. Right, the tutor means here. So after you inside the y equal to y box, you zoom in, you apply the formula again, but you should use the one that before, right before you see capital Z equal to small z. Okay, so what does this mean? I typically call it surprise, right? This is I will now call it additional surprise. Surprise, okay, due to z equal to small z. And this additional means what? Beyond, I know y equal to y. Y equal to small y give me some surprise, all right? But that surprise is already considered in this distribution. Now I'm zooming in further. I got this distribution. I hope you can think a little bit more clear through this way. Some people prefer this way, some people prefer just seeing the formula. Either way is fine. It's clear to me, but they require some time to practice. So now I'm asking you, if I do this loop, if the event is given like this, so suppose expectation of x given, first I see z, Then I see y. Is this the same as this? They are the same, okay? Given is given, known is known. So this all means, this doesn't have an order, okay? You can put either way you want. It just means those things you know for sure. It doesn't matter how you know it, which one you know first and second. Okay, it's just those numbers are known. These two are the same. Okay, you can compute different ways, they will give you the same answer. I think in the homework I asked you to do this. Did I? If I didn't, then I need to add more homeworks. You do these two ways, both in the recursive way, and you see they are the same. Okay. Okay, now let's get to our measurement update. If you know this fact, okay, now we can easily explain the measurement update step, which is the only hard part for Kalman filter. Okay. So you should first know our purpose. So our purpose now is that what? We want to compute xk plus 1 given k plus 1. And what we are given now, what we know now is the expectation of xk plus 1 given xk, yk, and its covariance. All right? And how to find the mean and the covariance of the new thing. That's the update equation. Okay, I will say again, this two approach, right? I'm going to repeat a little bit. Approach 1 is batch. Okay, we can do this find joint of everything up to k plus 1, right? So the joint will be xk plus 1, let's see, and the yk and the small yk plus 1. Do you know my notation? This is state. This is all the measurement up to time k. This small yk plus 1 here means the y at time k plus 1. Okay? And we can find this joint. I wouldn't write down the notation. It will be very complicated. Depending on how many k you see, it will be a very large covariance matrix with a long vector, right? Then we can use conditional mean formula. Because we know it's Gaussian, right? Conditional mean formula to compute what? Expectation of xk plus 1 given yk, and in addition to that, also given small yk plus 1. That's the best way. You just treat everything as giant Gaussian random vector, then given part of them, it's still Gaussian, you can use the formula, right? But that's not our goal. Our goal is trying to do recursive. The approach 2, as I mentioned, through the abstract example, I hope now at least you are a little bit more familiar with it. Recursive. Let's do recursive. Using what? The previous result. Xk plus 1 hat given k. We know it, right? Where do we know this? From the prediction step. And this is k, pk plus 1 given k. Using previous step to compute the new one, which is xk plus 1 hat and the pk plus 1. So in this case, first let's find joint. We want to rely on our previous measurement, updated belief, right? So let's see. First, we can find the conditional joint, okay, which is, I only care about current xk plus 1, a small xk, yk plus 1. They are related, right? So what I'm doing now, I'm using yk plus 1 to estimate xk plus 1, right? They are related, but given yk. So yk is given at time k. Now it's already in the here, right? Capital yk equal to small yk, and then it's already jumping to the next box. And this is, at time k, at yk given, capital yk is given, xk plus 1 and yk plus 1 are still random. Are you with me? You don't know them for sure yet. Okay, later you will know one of them for sure. So they are jointly distributed, and their distribution is, Xiaohan? Huh? 云天. They are jointly Gaussian, of course. Yeah, right. Conditional Gaussian is Gaussian, so they are still random. They are jointly Gaussian. I need to find their jointly Gaussian distribution, which is, let's say, the expectation of k plus 1 given capital Yk. This is the expectation of Yk plus 1 given Yk. Right? Any questions?
I think it's a linear transform, so it's
okay, in linear Gaussian case, in Kalman filter, everything is jointly Gaussian, no problem, right? I'm just trying to say, if we specify all, this is what? This is from Y0 all the way to Yk, right? If I specify all the measurements up to time k, I don't know for sure xk plus 1, and also don't know for sure about yk plus 1. Their distribution is still jointly Gaussian given yk. Okay, they're jointly Gaussian, so I can compute their, all we need to characterize Gaussian is what? Mean and covariance. So the mean, let's denote this mean is this, and this covariance, right? So there's a covariance of xk plus 1, I'll just call it that. Maybe that's fine. K plus 1 given yk. Everything is given yk. Covariance of xk plus 1, yk plus 1 given yk. I hope you can fill up the rest two terms. Let me write it down. Yk plus 1, xk plus 1 given yk. And this is the covariance of yk plus 1, yk plus 1 given yk. So at this k, at time k, xk plus 1 and yk plus 1 are jointly distributed. All right? So then, I want to say, now how do I compute these, the additional ones? I will say this is expectation of xk plus 1. If you want, I can define new variables, but I don't think that's, so at time k, let's define, okay? If we define, let's call it z. I think in the note I also do this. Xk plus 1 given yk. And the w equal to yk plus 1 equal to yk, given yk. What does this mean? Z and w denotes the randomness of x k plus 1 and small yk plus 1 given Guangzhou temperature at time k plus 1. So given capital Yk plus 1, the history up to k, both are random. Each of these randomness, I denote a new random variable. It's the same, all right? It's z and w, right? So I know z and w. If this helps you better, a Gaussian. Then this is this is that, okay? So you can view them as, if you don't like this conditional notation, you can view them as a new variable, okay? Conditional Gaussian is Gaussian, conditional probability is probability, conditional density is density. If you don't like the conditions, you can just remove them, define a new variable, okay? You just need to make sure the density are computed in the right way. Okay, then I will say expectation of z, which is this, given w equal to yk plus 1. By my notation, this will be e of z plus covariance of z and w, covariance of w inverse times yk plus 1 minus expectation of w. Okay. By my early notation, this is equivalent to say, let's not do define. This is nothing but z is what? Expectation of my expected measurement given yk. All right?
Z should be x.
Oh, this would be x, sorry. This is xk plus 1. Okay? So given capital YK, xk is random, its mean is this, right? And then I need to know how z and so xk plus 1 and yk plus 1 are related. But the relation I only care is relation given the condition yk is already specified. Okay, times the covariance of w is yk, okay, with yk plus 1 given capital YK. Inverse, right? And then times the surprise minus expectation of yk plus 1 given, given capital YK. Okay, let's call these terms different. This one is my term 1. This guy is my term 2. This guy is my 3. And what else I need? This guy, 4. If I know how to compute this 4, I know how to do this update. Okay, before you see any new measurement, this is your best estimate of xk plus 1. Okay, because that's, you already know by up to 10k, before you see any new measurement, that's the best. Okay, and your measurement will provide some information. Okay, so it's possible. Okay, it's possible that after giving yk, then the small yk plus 1 is very, very much deterministic, have very low variance. That's possible, or have larger variance. That's also possible. So that should be normalized, and how they are related. And those relations should be specified given capital YK. Okay. Now let's do one by one. Do you have any questions about this? I think we practiced many times, several times already. It's just nested conditioning. Let's do one by one. The first one is what? What is 1? Expectation of xk plus 1 given yk, but by definition, this is what? Xk plus 1 given k. That's my notation. That's given, right? Given by prediction step. This is already computed. We already computed this. This is known. That's my best guess before I see a new measurement. Okay, that has not related to measurement update. Now let's see how we can do the measurement update. Let's first compute. I don't think I have time to derive everything, so let's pick a few. Let's do the simplest one, which is the 4. Okay. Expectation of yk plus 1 given yk. What is it? We are trying to relate it to x, right? So that's the expectation of c xk plus 1 plus d uk plus 1 plus vk plus 1 given yk plus 1. Oh, sorry, given yk. Okay, because it's the expectation, I can move the constant things out. So that will be c times xk plus 1 given yk plus, is this 0?
No, it's constant.
It's constant. Expectation of a, I wouldn't say constant, sorry. Expectation of a deterministic thing is that particular deterministic constant, right? So it's d times uk plus 1. What about expectation of vk plus 1 given yk?
0.
It's 0. Okay? Little yk plus 1 is independent of capital YK. The new noise independent of previous noise. Okay, that's the assumption. And because we assume it's zero mean noise, if it is not zero mean, you need to subtract it, the mean, okay? But because we assume it's zero mean, that's 0. I hope you are fine with this part now. So this will be our xk plus 1 given k, right? So it's hat. Cxk plus 1 given k hat plus d of uk. That's our, let's pick one more. Let's do 2. Okay? So that's covariance of xk plus 1, yk plus 1 given yk. By the way, what's your understanding of this term?
What do you expect to see after
Yeah.
after you have the yk, the y value of yk?
Uh-huh.
But this may be different from what you really see as yk.
Yes. Okay. So typically, maybe yk, let's say 真正 temperature today. All right. And this capital YK is Guangzhou temperature up to yesterday. Right. And you see yesterday, temperature is pretty low, for example, 15 degrees, suppose. All right. I don't think that's the case, but anyway, let's suppose it's 15 degrees. Then somehow you lower your expectation of YK plus 1 today as well. Right? But this is on average, you expect to see some temperature of Shenzhen today. That's the best guess you can have, right? But later on, you may see a surprise. But that surprise is in addition to the surprise you already got from yesterday. So let's compute this covariance xk plus 1, yk plus 1, given capital YK. This is covariance of xk plus 1 with what? Yk is cxk plus 1 plus d of uk plus 1 plus vk plus 1, right? These two terms given yk. Okay. Okay, then you can do this by each of them, right? It's like a multiplication. It's indeed a multiplication. So why I carry this all over the place? Of course, that's condition. That means the density is the conditional density when you do the integration for computing expectation. That only means that, right? So this will be, what is this? Can you tell me the result? So covariance of xk plus 1 with xk plus 1 C transpose. That term, right? So this will be our, we cannot. Given is like the box I draw, okay? Given that everything changed, your belief about those variable changes. So that should be carried. This will be what? P k plus 1 given k, right? That's the definition of pk plus 1 given k times C transpose. Okay, that's the first term. Second term, what is it? Covariance of a constant is the constant? Is 0. Okay, covariance doesn't, this part is 0. What about covariance of xk plus 1 with vk plus 1? It's also 0. They are independent by our assumption, so this is also 0. Okay, overall, I have this term is pk plus 1 given k times c transpose. Very simple, right? That's our second term. Oh, I don't have space, so the third term I will skip. I don't think that makes more sense. You just compute this just like, I think you can do the calculation. We're done. This is common filter. Let's look at the formula. I will post the complete derivation. I don't think you care that much. I care, but I want you to at least go over the complete derivation every step, so you know roughly what's going on. And I wouldn't test you on the exam about derivation of the entire common filter, but I will test you on understandings. Okay. So if you look at the formula, let's look at the formula. Okay. This is the prediction step. You start with the estimate. I think all of them should have a hat. Okay. Where is it? That's it. So this is a hat. This is a hat. It didn't show correctly. This should be hat. Okay. So you start from some time with the best estimate you have at this stage. Then you do prediction. These are the prediction formula we derived last time. Does this look similar or familiar to you? These are linear prediction, just almost like a linear system, just ignoring the noise. This is the covariance update that we derived last time. Okay, and today we have been deriving measurement update. Look at the measurement update equation. What about this term? This is the surprise, the new surprise, the additional surprise, this particular step. What about, let's do some different color. What about this term? This is what? This should be, sorry, this is hat as well, right? This is expectation of yk plus 1 given capital YK. Cxk predicted minus, this is plus, right? If you have two minus sign. And you can look at your derivation, or our derivation before is this, right? C times this plus du. Well, the time index doesn't match that much because here we from k to k plus 1, that formula, it was from k minus 1 to k. That's the only difference. D of uk plus 1. So this is expectation that, right? If you look at this surprise term, it's hard for me to adjust. This term, right? That's a surprise term. That's so-called innovation. The yk minus the conditional expectation of yk plus 1. Sorry, the yk plus 1 minus the conditional expectation of yk plus 1 times how noisy that measurement is, and times the correlation between the y and the state. And these 2 and the 3 multiplied together will be our common gain. Okay, common gain matrix. So you look at this innovation term. This k is what? It's some constant times or some gain matrix times the surprise, and then gain matrix have the form of what? This guy. What is it? This would be covariance. Just the covariance update. Sorry, conditional expectation formula. This will be what? Covariance of xk plus 1 with yk plus 1 given capital YK. Okay, this term. I mean this term. Is it?
Yes.
So the reason I have ck is that allows c to vary every time step, that shouldn't bother. It's just this one we just derived. And the thing we're missing here is third term. Can you guess from the result? What is it? This is our third term that I didn't compute for you. I don't have space. It's very easy for you. Okay? What's truly missing from my derivation is this step that I didn't compute for you. That's the covariance matrix update. Following the steps I post online, you should be able to understand this as well. Now, I think you should have a very good understanding, maybe after some practice, of every single step in the Kalman filter. And I'm going to show you examples today, and you will see the codes are only less than 10 lines, as I promised you before. But if you don't understand them, you can only call packages. But now you understand them, you can do a lot of different things, including one thing that I hope I can cover today, is the extended Kalman filter. RK is just R for us. So the notation is here, right? Okay. Our notation is, this is that, sorry. Hat, everything given is hat. This is hat. RK is here. Is the measurement noise covariance. This is the process noise covariance, is QK. I allow them to be time varying. Okay, each time step, I need to multiply by A and B, but at different time K, I can multiply them by different A and different B. And their noise can have different covariance matrices. And derivation will be exactly the same. I just didn't carry over those sub-indices throughout the derivation. Okay, that's the whole notation. So typically, if you learn from online or other class, all you need is this. Okay, we can finish within one lecture. Now, I think you should know what exactly is going on and how to generalize them. What are the keys? Keys, I need to know the conditional distribution. And because it's Gaussian, so my conditional distribution can be characterized by mean and covariance. And if every step is conditional distribution, then next step will also be Gaussian, right? If the current step is Gaussian, next step is also Gaussian, right? So that's the Kalman filter whole algorithm. And I think you need some time to practice. Let's take a break and we'll come to a few examples next lecture. Let's continue our discussion. Okay, I think you should understand every single step in this update algorithm now. And now we're going to see a numerical example about Kalman filter. But before that, I want to mention one thing. So in simulation, any simulation environment, MATLAB or Python, you can generate random numbers. Okay. So for example, I can generate, I can let x equal to, for example, MATLAB notation, run n. Anyway, so I can generate 2 by 1. That means this is what? A Gaussian random vector. Okay, this all means is that x1 and x2, they are both uniform, they are both Gaussian random number, and with standard deviation equal to 1 and also 0 mean, okay? But if I put them together, they are independent as well. If I put them together, that means 0 mean. What about covariance matrix? If you think about them as random vector, it's 1, 1, 0, 0. Okay, that's the meaning. You can either generate them separately, and they're independent, so that's the covariance are 0, right? This is what covariance of x1 itself. Okay, so I can do this, but if I want to generate random vector that, suppose I want to generate V according to this is zero mean, and also with some covariance matrix R, how do I generate this? Modify X, so I can let V equal to square root of R times X, that's it. This is the matrix square root. Square root, which is only for positive semi-definite matrices, okay? If you read my linear algebra review, positive semi-definite matrices, okay? I think I explained a little bit about this. You can still take square root. Do you know how? Why it's the case? Or if you don't like this term, this will be like this. So it's R square root. It's the same. It's more, it's a matrix, by the way. Okay, it's just a matrix, R times this equal to R. You cannot take square root for negative definite matrices. Okay, so you will not have a kind of a real matrix anymore. So this is a square root matrix. You can just call square root of matrix in Python or MATLAB. That will give you that. Why is this case? Because covariance of V with V now becomes R transpose covariance of X times R transpose, right? And this is a symmetric. Covariance matrix itself is positive semi-definite. That's one property that we discussed. Is also symmetric, right? So transpose or not, they are the same. So that will give you that whatever R times identity, which is R. Okay, that's a typical way we generate random variables vectors with given covariance matrix. All right, with this specified, let's look at a Python example. This is the Kalman filter example. Let's take a quick path of it, right? Before that, I'm here trying to, what is it? It's already run. Let's clean out. Let's see. So here, I'm generating a matrix. The reason I generate like this is I just want to make sure I can specify their eigenvalues. I do a kind of random kind of T matrix, T diagonal T inverse, give me A, and that's so I know the eigenvalues of A are kind of stable A. All right. Here it's hold on. This is it's called the process noise, right? Process noise. Specification is zero mean and with covariance Q. I can specify how large the covariance is. That means how noisy this noise is, right? And what about R? R is here. R is here. So this is measurement noise. Measurement noise. And I specify some dimensionalities that I need to initialize my vectors. And so first of all, I'm trying to generate, here this part is, the goal is to generate data. In real experiments, you don't generate data, you get data, right? Here I generate data for testing purpose. I'll say generate data for testing. Okay, I initialize everything to be 0, and that just makes sure I have a matrix. And the way I arrange this matrix is X is a column vector, and each column represents a two-dimensional vector, right? And N is the number of steps I generate data for. Okay. Now I generate data. So here has nothing to do with Kalman filter. In reality, you will directly have the measurement. Here I just generate data. The way I generate data somehow follow my modeling assumption. First of all, I generate measurement noise. You see this thing? Square root m. LA is it's not Los Angeles, it's this guy, okay? Spice linear algebra package. This is LA dot square root, but m means matrix, okay? And the times the random numpy random dot run n. That's somehow.
I have some question for the data generated.
Yeah.
They are not actually follow the model because xk is already added noise, and sk plus 1 is generated based on that.
No, sk plus 1 is generated based on other different. Each k will have different noise. They are all independent.
So my question for Kalman filter is the xk plus 1 and the xk, their real value should follow a perfect model or not?
They don't have to. They don't have to. But here is perfect. Here is perfect. If you don't, if you have a question, we can talk offline about this. Right? So at process noise and measurement noise, and this is a measurement Cx plus measurement noise, and this is state update. I don't have a control here. Okay, we don't have control. I just didn't put a control for simplicity. And each k, each time step, I generate a new noise. This noise somehow is independent from previous generated noise. Somehow this is our, matches our assumption. If it doesn't match, it's fine, okay? X hat, that's begin our setup for, I say setup notation of variables for Kalman filtering, okay? X hat, X predict, K is the Kalman gain, and the P is the covariance matrix, P predict. I'm not sure whether you can, this is X hat, this is a P. And this is a P predict, this is X predict, X hat predict. I didn't say X hat predict, I just say X predict. All right, I initialize, I random pick a noise in this case. Random pick initial guess. It doesn't matter, it will eventually convert to the true one, okay? And I also random pick a covariance matrix at the beginning. Okay, I will explain this a little bit more after we see this example. And n is 100. Yes, n is 100. I don't need to redefine it here. Now I start Kalman filter. Let's count 1, 2, 3, 4, 5. 5 steps. That's the essential code for Kalman filtering. 5 steps. Of course, you need to set up variables. So don't be afraid of if you call package. There's some package called Kalman filtering. You call it, you don't know what's going on inside. And this may be what's going on inside. Just 5 lines of code, right? And X predict is A times X hat. What we are doing here, this is this step. Okay, X predict is A X hat plus BU. U is 0 in this case is just this, right? And then I do AP A transpose plus Q. So P predict AP A transpose plus Q. Now we can do the measurement update. We first compute Kalman gain. That's just P predict C transpose whatever inverse. Okay. Then XK. The next one is what? Is before you see the measurement, your best guess, which is the predicted one, times the Kalman gain times the surprise. Okay. And this is exactly what's going on here. Times the surprise, and then I update the covariance matrix to the next step. Okay, that's Kalman filtering. It will be very quick. Then we plot. In this case, I think X is how many dimensions? It's 3 dimensions. So I choose three things. Let's run it. So that's the. I think S2 is a little bit worse than the other cases. This is pretty good. It doesn't matter what I gave as the initial guess. Let's say this may be 0 is almost correct. I think I also use, I don't know why is this. Anyway, let me use my mouse. Let's use 1s, okay? It's wrong, right? It's completely wrong. My initial state was 0 when I simulate generate data. I think it should be okay as well. Let's see. It's still roughly the same, all right? It doesn't matter. You can see initially it's a big guess. As you see more and more measurement coming in, it follows the structure. It follows. It's kind of approaches the true state. Okay. What really affects the performance is the following. It's maybe, let's say, measurement noise. Let's say maybe we have more measurement noise. Just 1 times this. Okay. So if you run it again, it's become less accurate because your measurement it's too noisy, right? You don't know what the true state is, but still doing okay, right? And of course, the process noise, we can change them, but the more noise you have, the less accurate the system would be, right? I think that's about Kalman filtering. I want to briefly mention one thing in this case. Typically, here, you see the Kalman filter is a recursive step, right? From estimate to the predict, from predict to the measurement update, then you go on and on, right? So this is a loop. We can start this loop from either entering here. Entering this measurement step, you need what? In the prediction and the predicted covariance matrix. Entering this prediction step, you need the best estimate, okay, without the prediction. So typically, this one is typically easy to specify, okay? So for example, x0 given -1, it's given nothing. It's almost the same as this will be, expectation of this will be just expectation of x0. All right, you can input this guy to this and the covariance of x given -1. -1, suppose you have your first measurement come in at time 0. Given -1 means you didn't specify any information. You haven't given anything, it's unconditioned. So that's the initial distribution. And this will be the covariance of x0. Right? You can completely specify this. For this part, this guy is what? This guy, sorry, this is hat. This guy is expectation of x0 given y0, right? And the y0 is given. You need to compute a little bit before you can actually start the process. Okay, but I would say you see the simulation. I didn't care about this, right? So typically, I would say, I just mentioned, if the system, I'm not going to prove this, but I'm going to tell you, if a system A, Q, half, you should know all this notation now, right? If A, Q, half, Q is the covariance matrix of process noise. Taking half means square root of matrices. Why I can take square root? Because it's it's observable. Observable, okay? Somehow Kalman filter related to observability now, okay? If it is observable, then we can arbitrarily pick x0 head and the p0. It doesn't matter. Eventually, will converge. Okay? We can arbitrarily pick them, not necessarily the true one. Okay? But nothing is true yet, right? If that's the case, then it will eventually converge. It doesn't matter the initial estimate and initial covariance. You can pick them arbitrarily. Okay, I'm not going to cover this. If you're interested, you can. I can point you to the right literature about this. That will take more effort to prove. Okay, any questions so far? You see, the derivation take a lot of time. The example take a very, very, very short time. I think now without this asymptotic behavior, that's a little bit more advanced. This problem filtering step will be, I think every single steps should make sense to you now. Okay. Now let's jump to the Kalman filter extension, so-called extended Kalman filter.